All right, welcome everyone to this workshop on AI and debating. This is going to be part of a probably two-part series. The first one, this one is going to be mostly about the technical implementations of AI, trying to give you a better understanding and intuition of the way that this works under the hood. First of all, why should you bother to learn this? I think of course, the obvious argument here is that it's better to understand the world around you and know holistically how these things work because you want to understand the world around you and you want to be able to read the news as an educated reader. And of course, there's a real reason most of you are probably here. That is, you have figured out that a lot of motions these days are about AI, and namely the world final motion, for example, in Sofia. And you figured out that knowing more about AI is a very useful thing in debating if you want to win more debates, which is in of itself also a fair reason to learn more about this. What are we going to do today? Today, we're mostly going to be talking about data science principles and neural networks. The more practical considerations will come in the next part of the series. If you just want to watch that one and you want to skip all the technical mumbo jumbo, that is fine as well. Uh, just know that I do think it's useful because it gives you a better intuition, and hopefully, this talk should be under 30 minutes. I'm going to try to keep it as short as possible. And first, we're going to be talking about like data science principles to give you like an intuition of the way that computers learn from data and the world around them, and like from the very basics to the way that we now do AI, which is neural networks. Then the implications is mostly going to talk about what actually happens in the current world regarding AI and what are, for example, lawmakers' concerns. Then a bit on how to use tech spec, because as someone who does like STEM, I've figured out that there's a bit of a certain song and dance you sometimes have to do within debates if you want people to buy like tech spec, and you have to do this in sometimes a very specific way because otherwise they just don't buy you on your spec. So that I think is useful, maybe also for other STEM majors who still have trouble with this, because I know I struggled with this a decent bit. And then a bit of a tour of debate land, which is mostly how do we actually view this technology in debating? What is often said about it? How could you refute this or better or prove this better? And also some new arguments that I think can be useful in these classic clashes, for example, about AGI or about energy and water resources. But first, to get into the technical things. Um, let's say you want your computer to give you information, you want it to learn like a deeper relation. For example, about how much a certain resource costs, be this like meat, be this vegetables, etc. You have data, like you see in the graph on the left. You have data points that have a weight and an associated cost. Now the question is, what do we know? What can we learn from this graph? And what can we then do with that? What you would want to know here is you want to learn the deeper relationship from the data itself, which is imperfect, to better understand the world around it and the way what you can do with this. So, for example, if I learn the deeper relationship here between cost and weight, I can know without having like the specific data seen beforehand what something that's 110 pounds might cost, or even closer, like somewhere where we don't specifically have any data, like 52.6, for example, falls into this. We don't have any data. So technically, we don't really know what's going on at that point. But we can, based on the data, make an educated guess, right? And that's what we're here to do. First of all, we have to note that the data is imperfect. This is why you see like these gaps, right? When they have basically the same weight, there is still sometimes a decent difference in cost. This is due to something called random error. Basically, you have sort of the underlying relationship. This can be any type of function, any type of line, or whatever. You can just imagine this as some amorphous line in your head. But the data is not going to follow this line perfectly because there is a certain amount of error. So to put this in like a real world example with like measurement error. If you have like a very precise if you have very precise weighing equipment and you try to weigh, for example, a steak, you figure out this is exactly perfectly 5 kilos, and the price per kilo is $5. And then you put this on like the general butcher scale, which is not as precise. It's one time going to weigh like 4.98 kilos, and another time it's going to weigh like 5.01, etc. Uh, that all happens because of this random error. And this random error is something you don't actually want to know about, or you don't want to have, because it just obscures the real relationship, right? For example, in this case, there is a very clear correlation here, and it would be very nice if all of these points just lied neatly on a line. But no, instead, we have to sort of make an educated guess because the data is imperfect. Now, what is the way we do this? We do this by way of regression. And you can see examples of this on the right. The green one is a linear regression. The red line is a polynomial regression, because this is probably like a seventh order polynomial. Oh, for those who might not know that term, polynomial just means like x to some power. And this is probably like x to the seventh because you have all these kinds of parabolas together, right? Hmm. Now, question to the audience, which of these lines might we prefer if we're trying to learn the deeper relation between these two? Some of you may say the red one, some of you may say the green line. I think the most correct answer is the green line, but the red line is not necessarily wrong. That's to say, um, the red line perfectly goes through all the points, all the data points, like goes through them perfectly. So I understand why you might want to say the red line, because the green line actually has way more distance to these data points. This is something we would call training error. And you're very correct, like people who said the red line, you're very correct in the sense that you would generally want to minimize training error, because this is sort of the data that we have and that we're trying to train the computer on, in a sense. And and why would we not want to be as close to this as possible, right? Because the closer we are to the training data, the better we describe this relationship, because the data is there for a reason. The problem is random error. And quite often, when like your training error becomes too small, you're starting to fit on random error. And this in and of itself doesn't have to be horrible, but the problem is that due to the limitations of the methodology, this can lead to weird outcomes. So for example, you can see like a very clear trend trending upwards, right? All of this is like relatively reasonably around the green line. The green line might not be perfect, but it's somewhere around there. And let's say you now want to know what something costs at like zero point 0.5. According to the red line, you now get here, which, seeing as this is an increasing line, and this would be now have a higher value than any other data point we've seen before, quite unlikely that this is the correct explanation, right? And that's sort of the problem. Because if we want to fit too close to these data points, we get this incredibly complex function that describes this perfectly, but probably won't fit things that we haven't seen so far as well. Because it's trying to get as close to these data points as possible, and it doesn't really care about anything else. So it's very willing to make like a concession to have these like crazy peaks and what is the other, crazy peaks here. And that's probably a bad thing if you want accuracy. So that's why the green line is actually preferable. Of course, you can have this the other way around as well. This is where like a classic example, when you have like plotted data that really looks like a parabola, and then you just have a straight line through the middle. That's called underfitting. The red line is overfitting, so we're too close to the data points and we're missing the forest for the trees in a way. Whereas the green line in the situation where this would have looked like a parabola like this, um, then the green line would have been underfitting. Okay, now, how does AI work? We actually don't know. Nobody knows. And soon you're going to understand why we don't know what we know, or why we don't know that AI works. And then the question, are LLMs actually intelligent? Are large reasoning models actually intelligent? Again, nobody knows. Most signs point to no, but there's also very good signs, like them winning gold medals at math Olympiads, that point to yes. So jury's still out on that one. But really, how does it work? To understand how AI works, first we have to understand how complexer relationships are treated, right? So for example, like we just talked about like fitting a linear line. That's not that exciting. Let's do something more difficult, like trying to fit music, like to ascribe a music genre to a certain song. Now, let's say we have multiple different variables, such as energy, such as tempo. Sometimes we're able to find a relationship between energy and tempo that clearly divides these categories, such as here, right? You find this line, like energy as a function of tempo, or the other way around. And then you see that everything under this line is an R&B song, and everything above this line is a reggaeton song. That works beautifully. But if things are more complex and this relationship becomes nonlinear, or we need even more variables, then it becomes a lot more difficult to actually find this line. So the more complicated, like what you should take away from this is that the more complicated the input is, the more complex the output relationship is going to be, and the more flexibility that we need. This is why we got like the crazy polynomial in the first example, right? And you can also have way more variables because even music has a bunch of different things, like such as, hey, are people actually singing in like harmony? What kinds of chords are being used? In what octave are they singing? Is this actually singing? Is it more rapping? What is the tempo between words? Does it take a lot of pauses, etc., etc.? What type of instruments are there? All of these are just variables that contribute to the genre. So, and usually this is also not, there's not necessarily a clean line that divides these categories, right? This is very easy. This is not what it looks like in practice. This is also why people will disagree whether something is like rock or pop, for example. So usually we just describe these with like probabilities, and because that's the way we can make the best educated guess. That's correct the most often. Now, what are some of the problems with natural language that we have? Mhm. Natural language is almost infinitely more complex. First of all, we just have a bunch of words. I don't know how many the Oxford Dictionary has, but I seem to recall somewhere in the hundreds of thousands. And you also have very complex relationship, like context dependent. Down can just mean the direction going down. It can also mean to track down when it's used in conjugation with track, which means like to follow someone or to go after someone or something, right? It can also describe a mood depending on the context in which it's said. You also have context-independent relationships, such as fox and wolf, or dog and wolf, because we know that these share somewhat similar properties, right? Like fox and wolf are both wild animals, dog and wolf are both canines. Similarly, like mom and dad are both parents. It really doesn't matter what context this is set in for these relationships to exist. Then there's setting. You have euphemisms, for example, when you can't say something as directly as perhaps otherwise you would, but instead you have to word this in a more diplomatic manner. To understand why certain stuff is phrased a certain way, you also need to be able to do this. And like the computer needs to be able to understand setting. Then there's collisions. Words can mean the same thing, and the same word can mean different things. This is also something that's quite difficult to understand. And these are just the main problems. There's like many more. Now, okay, we have these sort of very complex relationships. how do we actually learn very complex relationships? How do we teach this to a computer? I think a good example here is image recognition. We understand cognitively that both of these are threes, even though this one's like white and this one is black, even though this one is tilted and this one is blurry and this one is clear. Doesn't matter, symbolically, we both recognize them to be threes. Again, this is a very complex relationship because you can't tell this by just matching pixels because almost none of them will match between these two, right? So how do you do this then? Because you can't just do like, oh, this pixel matches, this one doesn't, etc. That's not the way recognition here can work. No, it's about apparently like having this curve. It doesn't really matter what color these two are, as long as there's a clear contrast. This extra box around it doesn't really matter either, or that there's some dots here. The fact that it's blurry also shouldn't matter too much. It's more about the general shape and contrast, like having a curve here, a slightly more of a straight line here, and then a curve like this. These are all properties, right? Now, we try to get the computer to learn about these properties through neural networks. The way a neural network works is that you have, first of all, an input layer and an output layer. For the example with the threes, this means that in the input layer, you just have all the pixels, like all the values for the pixels. In the output layer, this means you have two. You have yes and no. And this is just like a probability that this is a three or probability that this is not a three. And then you have the hidden layers. The hidden layers are basically the way this learns and the way that it tries to learn these relationships. And each of these nodes in the hidden layer does not have a predetermined value. Like from the input layer, we give the first hidden layer its values, and then from the first hidden layer, we give the second hidden layer its values, and this in the end makes it to the output layer. The way we give these values is by taking the sum of the product of the previous layer's values and their respective weights. And this is why you see all these lines, we call them edges, going all over the place. Because this one has a line to all of these, and that basically describes this relationship, right? You take as an input, you take some coefficient times the value here, another coefficient times the value here, plus another coefficient times the value here, and the same goes for this one. And the values are like determined is like variable, right? This is determined by whatever input you put in. And then the sum of all of these, you add like some bias. That's a term we don't go into too much. That's just a mathematical thing. It's really not that relevant for the our purposes here. And some activation function, which is just nonlinear. Also not too relevant because this is just predetermined at the start of the train. It's about the weights because that's the one thing that the computer changes. It's basically in training trying to find a correct set of weights, like all of these numbers. So, for example, like two, three, four for this one, and then -8 for this one, for example. And through changing these weights, it's trying to minimize the error. That is to say, we first give it random weights, then we feed it all the images, so like these two, for example, and then we check, okay, what does it output? And we sort of say, no, we want you to minimize the error. So if it answered, no, this is not a three, and we do recognize it to be a three, then this counts towards its error. And it's going to like try to change one of the weights slightly in order to get less error. So for example, it says no to this three, and then we get, oh, now our accuracy is at 50% because it recognizes one and not the other. And then it's going to try and change this weight slightly, for example, uh, from like -8 to -9, and see whether this helps it recognize better. And if you have like a large data set, probably now you recognize a three more. So now you get to like 53%. And through making these small incremental steps in the weights, you're actually trying to get a better result. Uh, this these sort of small steps, small improvement, and then slowly moving upwards in performance is called local search. And it's a very well-known approach for tackling computationally intractable problems. Basically, problems that are very, very hard and we cannot find uh, the generally correct answer to. We just try to get a decent solution. And you can see, for example, like if you have on the x-axis some configuration of weights, and on the y-axis the performance, and lower is better, for example, you can see that we're moving this way, different weights, we are improving, we're improving. Oh no, and now we're stuck. So you need to find, sometimes you need to make it worse before it can get better. And this is sort of the problem with local search is you don't know whether you're going to find a better answer somewhere else. It might be worse for a second before it gets better. Or in this scenario, if you keep going from here on, you probably might never get better again. So you're just wasting time. And this is like a very simple two-dimensional thing. The reality looks more like this. And because you have all of these weights, which is all like an axis you can move on, right? It really looks more like a million dimensional space and trying to find like peaks in performance there, which is just very, very difficult to do. This is why we have these big ass data centers. They are really trying to do is trying to find a better set of weights. Then you have tokens and vector embedding, because just to quickly recap, these neural networks, um, they are able to learn. I forgot about this. They are able to learn actually some of the complex relationships. So they've tested this, and once you turn off, for example, this node in the example for the threes, you see that it can no longer accept blurry threes because this was the node that was sort of correcting for the fact that it was blurry. If you turn off this node, you can no longer have threes that are slightly tilted in their orientation, right? And so we can see that for relatively simple, these relatively simple examples, we can see that certain nodes are actually checking for properties that we as humans would also check for in trying to ascertain whether this is a three or not. And that's also the reason we can't really do this for LLMs, by the way, because 7 billion of these nodes instead of like a few thousand. So it's just very difficult to do. Um, so now we can sort of describe some of the very complex content-dependent relationships, right? Because, like I said, the threes, it only works context-dependent here because like I said, the contrast only works in relation to the stuff around the threes being a different color. So that's very context dependent, you could say. And this curve being part of a three only works if there's also a curve here and sort of a straight line here, right? So this is context dependent. And to describe context independent relationships, we use vector embeddings, which is also where we get the idea of tokens from and why we measure stuff in tokens. Because this is most of the computational work that that we actually have to do when you're querying an LLM. Basically, we have a bunch of properties, for example, 300, that we measure stuff on. And this is the way we try to get the computer to understand context-independent relationships. So, like I said earlier, for like dog and wolf both being part of canine, canine can be one of these dimensions or one of these properties that you can score on, sort of. So dog and canine would both get a very high score on canine, and a dog would also get a very high score on the pet property. But a wolf would not get a very high score on the pet property because very few people keep wolves as pets, right? Similarly, cat does not score very well on the canine property, but scores very high on the pet property. And this is basically the way we try to get the computer to slowly learn about these context independent relationships and what the world around us looks like. Because now we have it in numbers and then they can understand this. And they can understand now that if we're talking in the context of pets, We know that dog and cat score very highly on this, so we now attribute a much higher probability to these than we do to wolf, right? Then there's also some stuff on attention mechanism parallelism. Uh, Not as relevant for this. Like I adapted these slides from like a master's course that I helped teach at one point. Um, this is not as relevant for you guys, but basically, because we've learned that we can train computers in parallel, that is the reason this AI revolution has kicked off. And there's also the idea of some parts of a sentence are more important than others. So if you're talking like, I did not take the school to bus today, probably the word not is one of the most important words in that sentence because it inverses the entire meaning. And therefore, we should give high importance to that word. And modern LLMs also can do this prioritization, which also help them learn faster. The result of both of these, like learning context-independent relationships, learning context-dependent relationships between words, and being able to categorize words, has led us to where we are today. And the intuition that you have about LLMs now, which is just sort of a next word generator. So, for example, the cat likes to sleep in the. Now we have as input layer the previous sentence, and the output layer, it says to, but it's really all the words in the English language. Um, and it describes a probability to each of these. Sometimes they use like a slightly diminished version, of course, but um, and then you get like probabilistic answers. You cannot sleep in a zebra, so it describes very low probability to zebra, and it describes a much higher probability to box because this is something cats like to do, and that we've like described as a behavior of cats. So it describes a much higher probability to that. Notably, though, it does not say zero for zebra, which humans would definitely do. And it also does not describe zero to ability, also something humans would probably never say. Um, that is it for today. I am gonna do like the things to consider and the more practical things in the next session. I hope this was somewhat understandable. There's a lot of technical jargon and lingo that I used. It's also a lot of information to take in. You could probably take like several courses on like there's just entire courses about neural networks. So don't feel bad if you didn't understand all of this. It's quite technical and difficult, but I hope this gave you somewhat of a better intuition of how this technology works. And I hope that's useful. And I'll see you guys hopefully in the next one.